Okay. So just to start with a general setting, so that's the clock, the time that I have. Just to...
5 minutes before.
Okay, yeah. So just to start with a general context, well, what I mean by representation of measure is the following. So suppose that you are given a family of probability measures, mu x, and each of these measures are indexed by a set x, that in this case we choose to be a Riemannian manifold. And then these measures have support in another Riemannian manifold, M. So it's a family of measures parameterized on a Riemannian manifold, parameterized by another Riemannian manifold. And then what we call a representation of this family of measures is a mapping that takes the point x in X and one random variable in a space that it's not so important here, it's just one auxiliary space, and then returns to us a map, which is this T of omega and X on M, such that the push forward of this map on of the measure P on this space by the map is equal to the mu x. Okay, seems very abstract, and it is, but it will become clear in the context of dynamics. And then the question that we have in mind is the following. So which conditions we should impose on the measures mu x such that the maps T that represents this family has some regularity, for example. Okay? So, and this actually appears in the context of dynamics related to random perturbation of dynamical systems. And when I think of random perturbation, what I have in mind is like perhaps the most natural way of thinking of the random perturbations in terms of Markov chain. So the idea is that you have a dynamics that is generated by the iteration of a map F of M, from M to M, and it has some regularity. And then what we will do is to consider some family of probability or conditional probability distributions such that each of this pu epsilon has support near the f of x. And this epsilon is just considered as an amplitude of your perturbation. Okay. So the idea is that this represents, not in the sense here, but induce a random orbit given by the following. So you are given an xj, and then for the next iteration, you have f of xj. This will give you the xj plus 1. And then you consider that instead of having precisely the point f of xj, you get some, by chance, some values near this point with this distribution. Or if you like, you can think of this as x jumping to f of x, and then having some dispersion around this point with this distribution. It turns out that actually to do ergodic theory in this context, it's not so easy to look from this perspective. And what people usually do, starting, I guess, from Kiefer, is to consider the random perturbations in terms of a sequence of random maps. And the idea is very similar, but now you have your unperturbed dynamics generated by the iteration of f. You have a parameter that is just the amplitude of your perturbations. Sorry. And then what you do here implicitly is to assume that there is a probability measure on the space of the maps. And more than that, you want that this preserves some class of maps. Okay? So you are iterating your dynamics randomly, but preserving some property of what you want, some regularity of the maps. So in this case, what we want is that the support of each of this measure here is around f of x. So the random orbit here will be given by the iteration of these maps, where every f omega here is taken at random. And so this will generate a random orbit. And actually you can show that this is a type of Markov chain. So The opposite is more problematic. When you have a Markov chain and then you want to show that this is generated by a sequence of random maps. So in the context of dynamics, what usually this is used for is that you have, for example, for studying stochastic stability of your system. So you have a system, an unperturbed system, and then you consider some sort of perturbation, like either ways that I showed you before. And then the idea is that you have a physical measure, and you say that your system is stochastically stable if this measure that you obtained by the perturbation converges weakly to the unperturbed physical measure. Okay. Say again? No, the U is just where this should be the M. So it's, okay, thank you. Yeah. Okay. And so there are several people who have studied such problems. I guess it started with Sinai, looking at some of these properties of stochastic stability for, if I'm correct, for circle maps. Then there is like some long works by Kiefer, like looking at uniformly hyperbolic systems and expanding systems. And then there is also the work of Lai Sai-yong, almost at the same time as Kiefer, looking at uniformly hyperbolic systems. And then there are several others, Keller, Araújo, Alves, and Benedict and Viana for the Hannon family. So in general, the reason why we want to look at these problems in terms of random maps is because you need to have some properties, you need to handle some properties of the maps. So usually, implicitly, what you do is to assume that you have this probability on the space of the maps that you are looking at. And more than that, this, when you take the measures supported on the maps to the delta, or you reduce your perturbation to or when you take the amplitude of your perturbation to 0, the measure here converts to the unperturbed dynamics. And then there are several questions that are somehow interesting, but so far they are not answering many contexts. For example, dependence of the stochastic stability of or ergodic properties of these systems in terms of the distribution of the probability of the Markov chains, or relation to structural stability, for example, in terms of shadowing, and so on. So in this context, what we mean by representation of measure, what I wrote in the beginning as a very abstract setting is the following. So we say that the measure, the Markov chain is represented by the measure when you have such a property. You have this new epsilon in the space of the maps where you are interested to work with, such that for each of these steps of the Markov chain, you can choose the maps with the same distribution. And this is actually not such a new problem. I got to know about this actually in the book of Kiefer. In the first chapter, he talks about this, I think in 86 or the one in 88, I'm not sure. And he actually has a result in this, in this first chapter, but he quotes another work by Blumenthal and Corson, should be here, from the 70s, which is not the same who is here, and it's a bit too young for that, but no relation, so I asked it yesterday. And so what he showed is that in some conditions where the probability measures has full support in the whole space, you can construct a representation of these measures by continuous maps. Then Kiefer relaxed these conditions in 86, showing that it's possible to work when you have uniform uniformly distributed perturbation bounded around your unperturbed map, or the Markov chain, and you can construct measurable maps. Then there was the work by Quas in 91. So what he shows that if the densities of the Markov chain are smooth, and they depend smoothly on the point, on the base, or in our context, in the X, it is possible to represent these measures by smooth maps. Then Araújo constructs some random diffeomorphisms in his PhD thesis, if I'm not wrong. But the construction, it's for manifolds with trivial bundles. And this, the example that he shows relies strongly on this property of the manifolds. Then there is a construction of Benedict's and Viana for the Henon family when they prove the stochastic stability of the Henon family of maps. So what we try to do is to address this problem in the context that I put in the first slide, like a more general representation problem. And what we did was to use some transportation problem, to translate this into some transportation problem of measures and use some regularity of the transportations to induce the regularity of the maps that represent the measures. And I will try to explain a bit of the ideas behind. And so that's the result that we have. And what is stated there is that basically that if the measures, the parameterized family of measures, let me rephrase this. So if you have the measures supported in a manifold which is compact, oriented, and connected, and the manifold is slightly more regular than the densities itself, and the manifold, the manifold for the parameter has the same regularity of the densities, then you can get representation with the same regularity of the densities.
So what's the definition of representing again?
That you have this this map here in our context. Oops, this one. No? So there exist these maps such that the push forward holds uniformly on omega.
How does it relate to that definition?
Here?
The Markov chain?
Yeah, that was the whole role of the mu, and then you have that for each, you can take this f, and the push forward of the f with respect to this will be equal to this.
What's the connection between these two representations?
They are basically the one that I wrote before. And here, what we are supposing is also in the context of the dynamics that the parameter manifold is the same where you are interacting your map. In our general setting, it's not. You can go from one, take the measures that has the base on one space, and then you send the measures to another one. Okay, so, and no, you construct this along the proof, but it's not so important. For example, in some case, you actually can choose the omega to be the whole space, the whole M, or you can choose there are some ways that you can choose the omega to be the support of some steps of the measure, and then you normalize it. Okay. Okay, just to give some idea of the ingredients that we used, we actually started looking at this in terms of optimal transport problem. And the idea of optimal transport is that you have, it started with more like let's say a practical problem, that you have some piles of sand, and then you want to send to move this pile of sand from one region to the other, and you want to do this at minimal cost. So In terms of probability measures, what we want to do is the following. So you have you have a function C that is the cost, representing how much you spend moving from one region to the other, your mass, and then you want to minimize this, the cost of sending x to S of x, with the condition that one measure is transported to the other, which in our case means that the push forward of mu is by S is equal to nu. Okay, so this is a very nice problem. There are many applications in several areas, geometry and so on, but it's actually not always possible to solve such problems, because if you don't have the measures, for example, both measures here, if one measure, for example, is absolutely continuous with respect to the volume of the space and the other one is not, then the problem is already not well defined. So, and the alternative to deal with this is the following. You can look at some weak formulation of this problem, and this is due to Kantorovich. And the idea is that now you try to minimize the cost within some measures whose marginals are the initial measure mu and the initial measure nu. Okay. So this is a measure on the product space. But should be said more that this space actually here should be the admissible measures on the space. That means that the projection of this gamma into x is equal to mu, and the projection of gamma to y is equal to nu. Okay, this is a way to formulate this. And actually, going through some steps of some chapters of the book of Villani, for example, what you see is that this dual formulation leads you to the existence of maps that can transport one measure into the other, and these measures are actually given in somehow in terms of the gradient of some function, which I will not be more precise here about this function, but they are well defined. And then using the Jacobic equations, the condition that one measure is transported by the other, or the push forward of mu by S is equal to nu, leads to one PDE with a complicated shape, but it's treatable. And actually, the solutions of this PDE is related to this U here, which gives us the transportation map. So studying the regularity of the solutions of these PDEs accounts to studying the regularity of the optimal transport maps. Okay. But then this is what actually we have done in the beginning in the first work, but there is a price to pay here. And the price is that you need to ask for that the densities to be always bounded away from zero on the support of the measure, and you need to have some conditions on convexity of the support. And so this is actually bad if you want to deal also with measures in the case of bounded perturbations where the measures decay towards zero when it goes decays to zero towards the boundary of the support. Okay. So there is a way around, and the way is actually how the extra conditions that we asked appear. So when you have the one oriented and connected and compact manifold, you can actually use some older way of treating this problem that is due to Moser, and nowadays it's called Moser trick. And basically what it says is that if you have manifolds that are oriented, connected, and compact with the same volume and the same orientation. And then the volume forms of these manifolds are related. They are actually isomorphic. And the idea is that now we can use this to study a flow on the, that pushes one form into the other, and this connects the two measures that we are interested. Okay, so in our case, this flow for the time one flow for this volume forms on the case of Moser is the map that we are interested. And so then what we do here is actually to look for some, what we prove is like a kind of parametric Moser trick. So it's a way to define these flows which depend on the parameter of the manifold X. And then it really accounts to studying regular dependence of ODEs, just that the ODEs are maybe in a more complicated context in terms of vector fields there. And this is actually what gives us the map that is the transport map that we are after. And so the regularity of the dependence of the measures on X gives us the regularity of the map T that represents the measure. So I think it's, that's what I wanted to say.
Thank you very much.